For this video, we are going to look at one example of differential equation such that we are going to use the approach of Maclaurin series to solve this differential equation. At the beginning, we are given a first order differential equation dy over dx minus cosine x times y equals to secant x. And we are also given that when x equals to 0, y is equal to 0 as well. We are going to find the Maclaurin series for y up to and including the term in x squared. Every time when we are going to solve a differential equation, which means we are going to find an expression of y, finding the Maclaurin series for the solution, which means we are going to present the solution of the differential equation in the format of polynomials. Then by looking at this structure for Maclaurin series, we will be able to know that what we are going to chase, that will be the functional value when x equals to 0, as well as the first derivative value and the second derivative value when x equals to 0. As we just need to express our answer up to the term in x squared, which means we don't have to evaluate the third derivative or other higher order derivatives. At the beginning, because we are given that when x equals to 0, y is equal to 0 as well. So that for the step 1, we are going to write down this notation called y bracket 0, which is equal to 0. Then I would like to find the value of dy over dx when x equals to 0. So that I'm going to start from the given differential equation dy over dx minus cosine x bracket times y equals to secant x. Then we try to make dy over dx to be the subject, such that dy over dx on the left hand side equals to bracket cosine x times y and then plus secant x. And then when x equals to 0, we will be able to evaluate the following. That is, we can try to substitute both x and y by 0. That becomes cosine 0 bracket times 0 plus secant 0. Then we will be able to know that the first term must be 0, where secant 0, which means 1 divided by cosine 0, which is equal to 1. Then we will have this result. Next, we are going to find the second derivative when x equals to 0. To find the second derivative, that means we can try to differentiate once from the first derivative. Then we can refer to the third step here. We can differentiate both sides such that the left hand side would be d squared y over dx squared. But then in order to differentiate the first term on the right hand side, as it is in the format of a product, which means we have to apply the product rule. So at first we try to differentiate cosine x such that it becomes negative sine x. And then we can keep the small letter y unchanged. And then the next one, we are going to have the addition, and then we keep the cosine x unchanged. And then we are going to differentiate y, which means we will have another dy over dx. Up to here, this is the outcome from the product rule. And then right now, we are going to differentiate the second term on the right hand side, secant x. Differentiating secant x, we will have secant x times tangent x. Then in order to look at the case when x equals to 0, we can try to substitute both x and y by 0 on the right hand side. But then for this component called dy over dx, from the previous step, we already know that when x equals to 0, dy over dx equals to 1. Then we will be able to perform the substitution right now, that is negative sine 0 times 0. Of course, the result must be 0 for the first term. And then cosine 0 times dy over dx, which is equal to 1. And then secant 0, tangent 0. Because tangent 0 is also equal to 0, so that the first term and the third term will be 0. And then for the second term, when cosine 0 equals to 1, so which means the final value of the second derivative will be equals to 1. Therefore, the conclusion is y is equal to y bracket 0, which represents the functional value when x equals to 0, plus x times the value of dy over dx when x equals to 0, and then plus x squared over 2 factorial times the value of the second derivative when x equals to 0. But as we know that from the Maclaurin series, this is an infinite series, which means we have to indicate the notation plus ... every time. We have the functional value equals to 0, and then the value of the first derivative is equal to 1, and then from the fraction, 2 factorial is equal to 2, and then the second derivative value is equal to 1 as well. Therefore, y equals to x plus 1 over 2x squared plus ... which is in the format of an infinite polynomial.